Good evening, one and all. I welcome you all to the 10th live session of the NPTEL course Production Technology Theory and Practice. The tutor for this particular course is Professor Shona Kumar Chaudhary from IIT Kanpur, and I have been assigned the TA duty for this particular NPTEL course. So, in the last couple of lectures, we have studied extensively about the different conventional and non-conventional machining processes, whereby we have seen that in conventional processes there's a compulsory physical contact between the tool and the workpiece, and by imparting a relative motion between them, we are facilitating material removal by shear deformation of the workpiece material. Whereas in case of unconventional machining, there's no requirement for direct contact between the tool and the workpiece, and we have seen that the material removal can be facilitated by imparting different forms of energy, ranging from mechanical energy to thermal energy to chemical, electrochemical energy, or in the form of a beam. So it can be electron beam, plasma beam, laser beam, and based on that, we have seen there is a classification of the different non-conventional or unconventional machining processes. In the last live session, we have solved a few questions and numericals based on mechanical energy imparted unconventional processes, wherein the mode of energy through which the material removal takes place in the workpiece material is basically mechanical energy. So we have seen in abrasive jet machining or in abrasive water jet machining or water jet machining, this energy can be perceived as the mechanical and as the kinetic energy of the jet that hits the workpiece from a chosen standoff distance with given conditions of pressure or traverse rate. So based on that, we have seen the material removal takes place, and we have also come across modeling approaches through which we can predict the material removal rate of the uh, given process. After that, we have seen ultrasonic machining, which is essentially another form of unconventional machining, wherein we are imparting the energy in the form of mechanical energy. So there, the abrasive particle laden slurry is being forced through the gap between a vibrating tool and the workpiece. So due to this motion, what happens? The larger workpieces get hammered onto the workpiece surface. Larger abrasive particles get hammered onto the workpiece surface due to the to and fro motion of the tool, and due to this hammering action, the plastic deformation takes place, and material removal occurs at the surface of the workpiece. The tool also undergoes a little wear, and there are smaller abrasives as well, and these abrasives get impact motion, like they and by vibrational the vibrational energy of the tool is converted into the kinetic energy of the smaller abrasives by the impact motion. So that was another material removal mechanism in USM. The third one was cavitation. So, sorry, the third one was some chemical reaction-induced material removal. By choosing an appropriate slurry, we can induce some chemical reactions and aid in the dissolution of the workpiece material at the surface. And through the cavitation action of the expanding and the contracting volume of the slurry in between the tool and the workpiece surface, we see that the debris or the materials which has been removed from the surface in the form of small pieces. So they need to be evacuated from that region to ensure a good feature, or with a good with an appropriate standard of the feature and appropriate surface finish also. Today's session we will be in today's session we will be discussing about electrochemical machining and a little about electro discharge machining. Both has been both are being used in the industry since a long time. So coming to the questions, read the statements given below. In ECM, the tool wears out more than in case of electro discharge machining. That is EDM. In ECM, the electrochemical dissolution rate is more when the gap is less and vice versa. In ECM, the current density is directly proportional to the gap. Gap here means inter-electrode gap. And mechanism of material removal in ECM and EDM are different. The electrolyte in ECM is so chosen that the cathode is dissolved, but there is no deposition on the anode. So now we shall go one by one. In ECM, the tool wears out more than in case of EDM. No, that is a wrong option because in ECM we have seen that we have a cathode here. Sorry, cathode is negatively charged, negatively polarized, and we have an anode here, and in between that we have a static or generally dynamic electrolyte flow. Electrolyte dynamic means that the electrolyte here is flowing, so it takes away the debris which is formed over here as a result of the dissolution reactions. So here we have seen that material removal takes place only at the anode and material deposition takes place at the cathode under normal conditions of electrochemical reactions. However, we choose the electrolyte such that whatever ions are liberated from the anode surface into this. So suppose we have titanium here. So at the interface between the electrolyte and the titanium, we see that titanium ions sorry, titanium is getting oxidized into titanium ions and electrons. So they're getting these ions are getting liberated into the electrolyte. So there can be multiple options. These ions can flow across this interelectrode gap up to the cathode and get deposited there. This green color is the deposition. Or if we choose the material in such a way, if we choose the electrolyte in such a way that this titanium reacts with some species in the electrolyte to form a precipitate, and that gets carried away by this flowing electrolyte. So that is another outcome. So in electrochemical machining, we generally prefer that because we don't want this layer to form, because this layer won't allow the liberation of electrons. It hinders the reaction, and it reduces the rate of the you know the the rate of reaction, of the reaction kinetics. As a result of that, um, this electrolyte is chosen such in such a way these titanium ions are not electrodeposited here. Rather, they react with some species in the electrolyte and get precipitated. Yeah, so we see that there's no chance of tool wear out here. Some erosive action of the electrolyte may take away some tool material, but that's not a chemical or electrochemical reaction, so we can ignore that fact. However, in electro discharge machining, we see that workpiece is maintained as anode generally, and the tool as cathode. And we have a dielectric here. So this was an electrolyte. Electrolyte is a conductor. It makes up the circuit. It doesn't allow the circuit to stay open. Rather, since it is a conductor, the electrons and other ion species can easily flow through them, and it joins the circuit. However, here we have a dielectric. So what dielectric medium does is it will stop the flow of ions through it up to a given limit, up to a given potential, or say, which is also known as the dielectric breakdown potential. So beyond that, if the voltage is increased, voltage between these two electrodes, if it's increased, these dielectric molecules get ionized, and we get a column of ions here, which is also known as plasma. And due to the application of the this voltage, this is not a constant DC voltage. Rather, we give it as a pulsed DC voltage. I mean, this is just one type or waveform. We can also apply like this. This is the T on time, this is the T off time, and this is the voltage, say between 0 and V naught. We are applying this step voltage. So essentially, this V naught should be more than the dielectric breakdown voltage. So as we apply this for a small time, a large amount of energy is flowing in between these two, and I mean the ionic concentration here is very high across this channel, and this is manifested in the form of a spark. So this is nothing but a plasma column. Plasma is a column of ionized gas, and due to this spark, what happens? The material on the surface here, as well as here. So one thing that there may not be a single spark. There can be multiple sparks between the workpiece and the tool. Here. There can be this gap is very small. I've exaggerated it here. And interelectrode gap is much smaller. So we see that this due to this spark, the material here is getting melted and vaporized. So that's what we call as ablation, material ablation. And here we had seen only dissolution or oxidation, and here we see ablation. So ablation is a phenomenon where by providing some energy beyond the melting and vaporizing energy, the amount of energy required for melting and vaporization of a material. Due to this action, some a larger volume of material gets removed from here, and also smaller volumes also get removed from the tool material. So ablation is such a phenomenon which is occurring both at the workpiece surface as well as the tool surface, and you can't control it. That's why tool wear here is more. Tool wear in EDM is more compared to ECM. The first option is ruled out. Sorry. Yeah. Second option, in ECM, the electrochemical dissolution rate is more when the gap is less, and vice versa. So here you can see I'm removing this green layer since there's no electrodeposition happening. Ideally, no electrodeposition is happening. So this is the gap. that we're talking about here. So as current is flowing, if the gap is reduced, then the probability of the ions or the electron species which are removed here, them reaching to this particular cathode is higher. So that's why the current density it increases, right? So that's why we see that the current is same because the number of electrons that are flowing per unit time, that is same. However, the density of the current, that increases when the gap is less. Phenicium, the chemical dissolution rate is more when the gap is less. Yeah, so when larger amount of electrons are getting liberated, so it means that here dissolution reaction is happening at a faster rate, and hence more material is getting dissolved per unit time. So 2 is the correct option. In ECM, the current density is directly proportional to the gap. No, as the gap increases, the current density decreases. We see here that if this negative element, that is the cathode, it is kept at this position, it is not fed in this direction, rather it is kept at this position, then this particular gap is slowly increasing because the material here is dissolving, right? So suppose this is the time t1, this is the time t2, this is the time t3. So as rises, this gap increases, and as a result of this, the current density decreases. The number of electrons that are coming out here, them reaching to this cathode. I mean, not only the electrons and the ions that are liberated, them participating in the entire reaction, that probability decreases when the gap is more, and hence the current density it decreases. So it can be no way directly proportional to the gap. So 3 is again a wrong option. Mechanism of material removal in ECM and EDM is different. Yeah, we have already discussed here. Here it's dissolution by means of oxidation. Here it's ablation under uh, the application of sparks. 4 is again a correct option. The electrolyte in ECM is so chosen that the cathode is dissolved, but there is no deposition on anode. It's just the opposite of what we have seen. The anode is getting dissolved, but there is no deposition on the cathode. So 2 and 4, C is the correct option. Coming to the next question, which of the following is the primary function of electrolyte in ECM? We have already discussed this in the previous question. Completing the electrical circuit, yes, because electrolyte is conductive, it contains ions, ions are present, they allow the conduction of electricity. Sustaining the required electrochemical reactions, yes. Carrying away the generated heat or waste product, this is also a correct option because it is in liquid state, and as we are flowing it between the two tool and the electrode, sorry, tool and the workpiece, uh, due to this flowing motion, the it is carrying away the heat that is being generated here and as well as on the tool due to the electrochemical reactions. And also waste product here means the debris which is generated, I mean the material that is removed here, or the corrosion products that are found here, so they need to be carried out, I mean they need to be liberated from this workpiece surface, so that is done by the flow of this electrolyte. So all of the above is the correct option. Okay, if you notice another thing here, if this is the tool, this is the workpiece, and here we have electrolyte. The current density here along the central region. The flow path of the current, it need not be necessarily here in this within this column only, within this in space only. There can be some stray currents like this, because we are seeing that this part of the electrode is also exposed to the electrolyte, so that is also taking part in the reaction. So what happens, suppose this is the feature size that we are expecting after the electrochemical machining, that happens more like this. So this is due to the stray corrosion actions, some overcut happens. And this was the original dimension, like you wanted like this, but what you got is slightly deviated from that. So this is what we call a stray corrosion zone. Another thing, if you notice carefully here, suppose we are drilling a hole through by ECM. So this is my cathode after some reaction, after some time of reaction, and this is the workpiece. So initially it was like this along this dotted line. Now after the initial reaction, it has come down. Now you see that this portion of the cathode, this two walls of the cathode are also exposed to the electrolyte flow. Electrolyte flow is happening like this. So what happens, the current flows in this direction also, and as a result of that, material is getting removed from here also. We want material removal along this depth, but as a undesirable outcome, material removal occurs in the lateral directions, the transverse direction also. So that is something we don't want. So to prevent this, we generally, suppose this is the cathode we have, we keep this surface open, and we put insulator, an insulating jacket around it, and we also circulate some coolant through it if it's required at all. If it's not required, then we don't do it. So this is insulated jacket, and this is the metallic, or the conductive rather, conductive end. So if this tool is being used here, then this lateral machining is not happening. Let's solve a numerical based on ECM. So you have an iron workpiece which has been chosen for ECM, which will be machined using ECM. The material removal rate that is desired is 4 centimeter cube per minute. So you have MRR, that is volumetric material removal, is 4 centimeter cube per minute. The gram atomic weight, valence, and the density of iron are given as follows. So 56, if you try to recall, then the unit for atomic weight is gram per mole. Then you have valency of iron is 2, which means that this reaction is happening. Okay. So for one atom of iron to get dissolved into the electrolyte to form one bivalent, iron electron, sorry, iron, Fe2 plus ion, ferrous ion, two electrons are getting liberated. So that is the meaning of this valency. And as you can see that this is an important factor to be considered while modeling the MRR. And then you have density 7.8 gram per centimeter cube. So you need to calculate the current that should be provided into the circuit to achieve this given MRR. So from Faraday's law, we know that the mass of the material removed, that is directly proportional to the charge flow between the two electrodes, that is the anode and the cathode. So Q, and again mass of material that is removed or that is taking part in this particular reaction, that is directly proportional to the electrochemical equivalent, which is nothing but A by, this should be V here, A by V, that is uh, atomic weight divided by the valence. So combining both, we can write, and yeah, Q can be written as I into T, which is current into time. So Q is nothing but the charge flow rate, the number of charges that are flowing for. Sorry, Q is the total amount of charge. Small q is nothing but the dq by dt. So over a time span of t, we can write q is equal to, capital Q is equal to q into t. So this q is nothing but current I. So q is equal to I into t. Anyway, so we have here is m directly proportional to I into t into a by v. Now if we bring t to this side, then m by t is, we introduce a constant here, which is also known as Faraday's constant in the denominator, 1 by Faraday's constant rather. So mass can be written as, yes, mass can be written as volume into density, right? Density of the material that is taking part in the reaction. So V by T is nothing but this material removal rate, volumetric material removal rate, which is equal to I into A by V divided by F into rho. Now if you plug in the values, then you should also be attentive with the units. 4 centimeter cube per minute, and here also you have something centimeter cube, yeah, gram per centimeter cube. But minutes should be converted to seconds because this time, um, yeah, like time should, yeah, this Coulomb's constant is not unitless, rather it is carrying some units. So that is in SI. So you need to convert it to second. Equal to I here. You need to calculate I, right, into A by V. Yeah, 56 gram per mole divided by 2. F is 96500 into rho has been given as 7.8 gram per centimeter. Now if you do the calculations, you will find I is coming out to be 1792 amperes. So this was a simple numerical where if you could recall this particular formula, then you just substitute the values and you will arrive at the end result. Coming to the next question. So in the previous one, we have seen what how to calculate the MRR for, how to predict the MRR for um, element. I mean, for a metal which is which is containing only one element, like it can be iron, it can be titanium. However, in day-to-day applications, we come across different alloying systems, different alloys, and we are using this unconventional machining because there are some restrictions, some drawbacks of conventional machining on some hard to machine materials. So We generally remove them using ECM, EDM, all these unconventional processes. So they are such materials are not single element materials, but they are alloys of different elements, constituent elements. So one such alloy is nickel superalloy, used in aerospace applications and high temperature applications, high strength, high temperature applications. So nickel, it contains nickel 70%, chromium 20%, iron 5%, and the rest is titanium. Then suppose we are doing ECM on this. So now you have a standard tool electrode setup, and you have a flow of electrolyte here and this. Now you have said that the area of the tool, which is nothing but this cross section area, is 1500 mm square, and the current of 2000 ampere is flowing in between this gap. It's 2000 ampere. Assume this is basically I. So assume dissolution to take place at lowest valency of elements. So these are the lowest valency of elements that have been specified, and also the atomic weight and the density has been specified. We can understand that you can't directly apply this formula here because you have a set of A and V given, and you have a set of rho given, right? So you can't directly calculate MRR by using this. So we need to find out something which caters to all the A by V values for all the elements, and this rho should be adjusted in such a way like it should be for the entire alloy. Okay. This also for the entire alloy. How to evaluate that? So there's a very small derivation. Just if you are curious about it, then so the total mass that is being removed, that is a summation of the individual, the mass of the individual elements that is being removed. I is you can write it like this: m of nickel plus m of chromium, m of iron plus m of Ti. So these are all the mass of the individual elements that are taking part in the electrochemical reactions, and they are being converted from the atomic, from the atoms to the ions, okay, through this electrochemical reaction. Okay, so you can write it as an fraction, as an atomic mass fraction, alpha I into m total. This is nothing but mi. So summation of that will give you m. Sorry, this is not atomic mass fraction. This is mass fraction, alpha I. So now from Faraday's law, you know, mi for the ith element, qi into ai by vi divided by the Faraday's constant f. So what is qi here? We have seen in the previous problem. Qi is the charge flow that is contributed from the ith element. Ith means either from like nickel or chromium or iron or Ti. Okay. So suppose this is 1, 2, 3, 4. So Q1 is the amount of charge flow that is contributed by nickel. Q2 is the same for chromium. Likewise. So from here you can write Qi is nothing but Mi into Vi by Ai divided by sorry, into F. Now you substitute Mi here. It's nothing but alpha I into M total into Vi by Ai into F, right? So we know that the summation of Qi is the total current is I into the time of machining T. Okay. Now all we do is just substitute Qi here. So we have summation of alpha I into M total into Vi by Ai to F equal to I into T. So MRR is nothing but M total by T, which is equal to I divided by F into summation of alpha I into Vi by Ai. Okay, so this is for an alloy. So in the question you have been asked about the rate of dissolution. So rate of dissolution here means hmm, the depth, the depth that is being machined in this direction, y direction. So it's basically dy by dt is the rate of dissolution here. So it's nothing but the volume that has been removed. So this much volume is being removed divided by the area. Area means this cross sectional area. So it is nothing but the volumetric MRR divided by the cross sectional area of 2. So here we assume that the feature size that we are getting here, it is same as that of the tool. So in practically that doesn't happen, but here we are assuming like that. So we need to calculate MRR V. That means so MRR V is nothing but MRR into rho of the alloy. Sorry, MRR divided by the rho of the alloy. What is rho of alloy? Okay. Rho of alloy. It's the total mass of the alloy M divided by the volume, total volume of the alloy V. So V can be again written as the summation of the volumes of the individual elements of that alloy. So that again can be written as, so we know that mass by volume is equal to density. So V is nothing but mass by density. So it's Mi by rho I. Rho I is the um, density of the ith element. So again, Mi can be written as alpha I into M. So that M and this M will cancel out. So what we will be left with is 1 by sigma alpha I by rho I. So we have rho of alloy is equal to 1 by alpha I by rho I. If we substitute it here, then we will get MRR V is equal to I divided by F into Vi by Vi is the valency of the ith element, and Ai is the atomic weight of the ith element. Now all you have to do is evaluate these summations for the elements, each element. So from here we will get the alpha I values. Alpha nickel is 0. 0.7, alpha chromium is 0.2, alpha Fe is 0.05, the remaining is titanium, which is 9, or it's nothing but 0.05. Okay, and you have here the AI, Pi, and rho I. So all you have to do is substitute the values here. Okay? So I'm just writing the entire statement here. Alpha nickel by rho nickel plus alpha chromium by rho chromium plus alpha iron by rho of iron plus alpha titanium by rho of titanium. And similarly here you have alpha nickel into valency of nickel by atomic weight of nickel plus alpha chromium valency of chromium by atomic weight of chromium, and similarly the other two elements. If you do all the calculations, then you know I, you know Faraday's constant, you know all these individual values, and you will arrive at 2140 mm cube by minute per minute. So this is the volumetric material removal. Now you have to find out the rate of dissolution. So that is nothing but 2140 divided by the area of the electrode. Cross sectional area of the electrode is been given as 1500 mm. You should be careful about the units. So it's 1.43 millimeter per minute. So this is my final answer. Okay. So that was it for this particular numerical. You just need to know about how you are either you can memorize this one, this expression, knowing how it is how you are arriving at it, or you can just work out this small derivation and arrive at this expression. In electrochemical machining process, the ratio of the material removal rate to tool wear rate is how much? So again, in ECM, there is no significant tool wear. Okay, so we see it's due to the mechanism of the material removal in ECM that the some material can get electro deposited on the cathode under some unforeseen circumstances. I mean, undesired circumstances. Because in ECM we don't want the deposition part to happen, but still, if the electrode or the tool is very close to the machining region, suppose we are doing some micro ECM process, and this IEG is very less, and the electrolyte flow somehow gets hindered here due to the formation of some debris or some small particles in the electrolyte. Generally, we are filtering the electrolyte and then circulating through this. Still, if some foreign particles are here and the gap is very less, then this then some amount of this electrode deposition may occur at this surface. Some layers may be formed on the cathode surface, and that hinders the reaction kinetics. So anyway, that is an exceptional case. But ideally, the tool wear rate is zero. So something by zero is infinity. However, in place of ECM, if you had EDM, then it would have been some positive quantity, which is obviously more than one. This ratio would have been more than one. But TWR is not zero because due to the spark that's happening between the tool and the electrode, some material at the tool surface is also getting ablated due to this energy, and as a result, small pits are forming there also on the surface of the tool. We generally choose the tool uh, in such a way that its melting point is very high compared to the that of the workpiece, and second of all, it's hard. So like that, we choose the tool material, and obviously it should be conductive. So in ECM and EDM, the basic prerequisite for machining is that the workpiece material should be electrically conductive, because we see that the flow of electrons facilitates the material removal mechanisms in both the processes. Another alternative of EDM is ECDM, electrochemical discharge machining. There we can see that non-metallic materials can be also machined. Workpiece is connected to the positive terminal in an electrode in EDM process. So why so? So we have the tool here, we have the workpiece here. So generally this is positive, this is negative. Again, if we revisit the mechanism of EDM process, or the process physics rather, mechanism or process physics of electrode discharge machining. What happens when you are passing some electric current through this circuit and you have a dielectric medium here? We have already discussed what's dielectric and how is it different from electrolyte or insulator. After providing a given a voltage beyond the given threshold, it breaks down, and suddenly there's flow of ions. But below that voltage, there's no flow of ions because the dielectric doesn't break down. So we see that the voltage signal here is not a constant but a pulsed voltage signal. What happens in this region, in this particular t on time, when there's a flow of current? I mean, flow of current means that the potential here is maximum. That is, say this is V naught here between these two electrodes. The electrons are slowly flowing from this surface to this surface in this direction. So as the electrons are flowing through the dielectric medium, it is ionizing the dielectric molecules and dissociating them into ions. These are in molecular form due to the um, collision with the electrons. They are dissociating into ions. The molecules are dissociating into ions. So this happens continually. Like you're seeing that this particular part where the voltage increases from 0 to V naught, that is not a straight line, because if you see along the time axis, it happens like this. Maybe it is steeper, but it is not a straight line, because that takes some finite time to reach the voltage from 0 to V naught. So during this time, and also here, the dielectric medium is getting ionized. and this happens very fast. So suddenly, beyond this VD, that is the discharge voltage, oh sorry, the dielectric breakdown voltage, the this particular process becomes prominent, that by the ionizing action of the electrons, the dielectric molecules are breaking down into ions, and there suddenly a large volume of ions in this channel, in this particular region. As a result, a spark is generated here, and due to this spark, the material on the surface of the workpiece, as well as in small portions of the tool, it's getting melted and vaporized. That is what we call as ablation. Now, if we see here that most of this uh, material removal is taking place by the impingement of this electrons, which are flowing at high velocity from this negative terminal to the positive terminal. Electrons, as well as some negative ions which are formed from this dielectric medium, and the positive ions are uh, going towards the cathode and hitting it. Okay, so we know that the kinetic energy of the electron can be written as half into me into V squared. Electrons or ions, whatever, E or I. So we see that this kinetic energy is only like converted. Like we can say that higher the kinetic energy, higher will be the discharge energy. So we see that this electrons are hitting the workpiece surface at a very this K. It's more predominantly affected by this velocity rather than the mass of the charged particles. So electrons have lower mass, but they are accelerated to a very high velocity. So it's since it's V squared term, so the kinetic energy of the impinging electrons is also very high, and the spark energy is also high. So that's why it facilitates a larger rate of material removal. On the contrary, if we would have put it at opposite polarity, suppose the tool was kept at positive voltage and positive potential, and the workpiece at a negative potential, then most of the electrons would have flowed from the workpiece towards the tool. So more amount of energy would participate in material removal at the tool rather than the workpiece, while only a few of the positive ions which are liberated due to the dissociation of the dielectric will be hitting on the workpiece in this case. So the material removal will be very less here, and the tool wear rate will be very high. And this is obviously something that we don't want. So that is why we connect it to a negative terminal, and the workpiece to a positive terminal. So larger material removal rate. Okay, that's it for today's session. If you are having any doubt, you can come up with them, or you can also post them on the portal, and they will be addressed by the team. Thank you for joining today, and we will be meeting again next Friday. So today was an exception because I was not able to take last yesterday's class, and that's why it was rescheduled for today. We'll be meeting again next Friday. Thank you.